Thank you for joining today for the presentation about the value of open source short-term energy forecasting demonstrated to real-world use cases. And so I'm Bart Pleiter, I'm from Alliander, and I'm here today together with Maarten van Doorn from Sigholm. And yeah, like the title says, we will talk about use cases from openSTEF from two completely different perspectives. But before we get into that, I think we first need a very brief introduction on what is openSTEF. So openSTEF is, or stands for Open Short-Term Energy Forecasting, and it's a Python package that allows you to create these short-term energy forecasts. And when we're talking about short-term, we're really talking about hours until days ahead into the future. And so also good to mention, openSTEF is not just a model, it's actually a complete Python package or framework that really does all of these steps needed to create accurate energy forecast. So from data pre-processing to feature engineering up to post-processing and evaluation, it's all in openSTEF. And yeah, I'll first talk about how we use this in Alliander. So Alliander is one of the largest grid operator DSOs within the Netherlands. And we have quite some congestion issues in the Netherlands. So as you can see here from a quite recent picture about transmission capacity, you see that the electricity grid in the Netherlands is quite full. So there's not much room left for new companies to be, or schools, or well, any customer basically, to be connected to the electrical grid. And so this has quite some consequences. So we have quite a large waiting list of customers that we want to connect to the grid, but we cannot because of the grid being full. And this can have, this actually has quite some societal impacts because both schools and large companies, so this really has quite some impact on the Netherlands. And so we want to solve this issue. And there are multiple approaches you can take to still connect these customers to our grid. So the most obvious one would be to just expand the grid, put more cables in the ground, build more transformers. And of course, we're doing that, but that's something that takes quite some time and is also quite expensive. So this does not really solve the issue we're having right now. So we also want to do a different strategy where we better utilize the grid that we currently have. So given the amount of, given the asset, the grid that we currently have, how can we connect more of these customers from the waiting list? And so one way to do that is using congestion management, and that's really a short-term solution. So what we then do is we take some customers from this waiting list, and with flexible contracts, we can still add them to the grid. So we ask a little bit of flexibility from them, so we can have some say into certain moments to limit the energy usage. And that also brings us to the first real use case, so this grid congestion forecasting. So what we then have, when we add these new customers to the already full grid, we will have moments where the grid will be overloaded at some point. So what we then do is we forecast these points into the future, so 1 or 2 days ahead. And there you can, for example, see that, at the second day here, there is a peak that, it basically means the load will exceed the limit of this asset. And what we then can do when we detect this 1 or 2 days ahead, we can contact this customer of which we had a flexible contract with and say, hey, we see there is a peak. Can you reduce your energy usage that moment? And so what will happen then is in the future, they will, when that moment arrives, they will, limit their energy usage and we will prevent this peak from happening. And the only way to do this in a proper way, in a safe way, is to have accurate forecast. And so that's where we use openSTEF for. And we also can take this to the next level, basically. So that's something we're also doing, not just looking at individual assets of the grid, but also looking at MV routes. So a bit of background, what is an MV route? So that stands for medium voltage route. It's basically a part of our distribution grid that helps us to distribute power from the primary substations to the customers. And so what it basically contains is it starts at the primary substation and then connects to large customers allows to connect large customers directly to medium voltage, but also secondary substations, which is the entry point to the low voltage grid. And we typically have measurements at all these ends of this MV route. So at the start, at the primary substation, we have measurements from these large customers. And we also have some way to measure these secondary substations. And the thing what we want to do with these routes is we also want to monitor the cables that connect all these parts together. And we have many of these cables, and they're all underground. And it's not really easy to just measure them. So we use an alternative strategy. So by knowing how everything is connected, so knowing the topology, and having these measurements at all these entry and exit points of the route, so we know what goes in the route and goes out of the route, we can actually use a different LF Energy project called the Power Grid model, who will also be speaking today, so look forward for that if you're interested, to do state estimation and see what is the power flow that goes to, that flows through of these cables. So we can still monitor each of these cables. And we're using that for 2 use cases. So the first one is for real-time monitoring of these routes. So we want to know in real time what happens at these cables. And then you would think, why would we need short-term forecasts for that? Well, it's actually because not all of our measurements come in at real time. So for example, these large customer measurements, they go through an external party, and we have like 1 or 2 days delay of that. So that means we cannot do real-time monitoring, but using openSTEF, we can forecast those measurements well into the present. And we're currently doing that in production. And furthermore, we're also looking into extending this to do just like on the previous slide of the previous use case, to do this on a day ahead scale. So there we can really see 1 or 2 days ahead. Will there be a peak? And can we activate a flexible contract to reduce this peak from happening? And yeah, this is quite interesting use case. And there is actually a paper published about this, or being published. It's being accepted by Sigholm. It has been accepted, but it's not like publicly available on the internet yet. So keep an eye out for that if you want to learn more about this use case. And then a different way of doing net congestion, where we also need these forecasts for, is for free space forecasting. So when we say the grid is full, we do not mean that the grid is full 24/7. So when you look at the typical usage of the grid for a given day, then you usually see that there's like one peak moment that really limits what can be connected to this asset or to the grid. So here, for example, during evening when people come home from work, they start to charge their electric cars, start cooking, really do a lot of, well, using a lot of electricity, and that's the limiting factor. But when we look at these other moments, there's quite some room left actually, or some capacity left. So we want to also better utilize that. So something we do is we use these short-term energy forecasts to predict when will there be some unused capacity, and then we can assign this to charging point operators to help them charging more electric vehicles, more of them and faster. So that was it for congestion use cases. So these are the more typical use cases you would see at the DSO. But we're also doing something else, and that's sending transport forecast. So we, as a DSO, we need to distribute power to customers, but we actually are a customer of the TSO, which does the transmission of power, which is, in our case, in the Netherlands, is TenneT. And what it basically means is, well, we're one of their customers, and just like large customers have to send their transport forecast to us, so what they expect to be using from our grid, we also have to do that to TenneT. And we have to do that at these specific coupling points. And why do we need to do this? Well, it's basically to help TenneT, the TSO, which has many customers aside from us as well, to help them in their safety assessments of their grid. So we can help them by saying this is the amount of power that we expect to draw from your grid at these points, help them to keep their grid safe, basically. And so at all of these coupling points, these points where our grid is connected to TenneT's grid, we send daily prognosis for up to 2 days ahead. And that's also something we use openSTEF for. And there the focus is also quite different from these congestion forecasts, because with these congestion forecasts, the focus is really on these peak moments. So the models within openSTEF for congestion forecasting is also really focused on predicting these peaks well and not so much these other not interesting moments. But for transport forecasts, you want to have a quite accurate forecast of, well, at all time points. So that's also where we can use openSTEF or with a different model and different settings to create more, better forecasts for these use cases. And then finally, another use case that we're using openSTEF for is for grid losses. So, well, we are DSO, so we distribute forecasts, but we're not really like using power or electricity. We actually do use power in some way, in that our grid, well, it's not perfect. Like all cables and transformers, we have grid losses, and this adds up to quite a large amount of energy. And this amount of energy we have to, well, basically buy on a day-ahead basis, and then well, the amount of power that we then actually use in terms of these grid losses is what we have to compensate for on the imbalance market. So there goes quite a lot of money on this. So what we do is we basically then forecast the entire load of our grid area, which is this blue area, so 1/3 of the Netherlands. And then we take a few percent of this for the grid losses, and we use that strategy to well, basically for buying the electricity to compensate for our grid losses. And there you see it's a quite different problem. So you have a quite aggregated signal with really different characteristics from, for example, individual customers or secondary substations or lower in the grid that you would typically use for congestion management. And there you also then see that different features are more important, like when it's a holiday or not. And so the focus is also quite different for this use case, and therefore we also have in openSTEF spent quite some time to also make forecast quite well for these more aggregated signals. And it then also brings us to like the conclusion or the summary of like the Alliander use cases. So we saw three large use cases. So this congestion forecasting, for transport forecast, and for grid losses, and all of them were quite different in a way that. In terms of aggregation level, so at which point in the grid you need these forecasts for. So we saw for these congestion forecasts that you really need to forecast sometimes for the individual customer to see how much can they help with reducing the congestion peak that you predicted. Or at substation level, also for the transport forecast, or even entire grid areas for grid losses. And for all of these we use openSTEF and are quite happy about it. And with that, I will pass it over to Maarten, who will talk about, well, quite different use cases.
Yes, thanks, Bart. So I'm Maarten. Used to work also in the team with Bart on openSTEF, but 2 years ago I moved to Sweden, and now I'm working with district heating. It's quite cold up there, a lot of heat demand. So who of you know district heating? Maybe you even have your home heated with district heating. Raise up your hand. Quite a lot. Really good. In the Nordics, this is quite a common way of heating your house. So basically this is central heating for the city. So it's instead of heating each home separately, there is a central production facility for the heat, and the heat is distributed with a grid. So it's not copper that's in the ground for this, but just pipes with water that are transporting heat throughout the city. So how does it work? I have a very simple picture here. So there is this central production facility transporting water through the ground, through the streets, so pipes in the street, to a delivery unit in most homes, and there it is actually has the same function as maybe a gas boiler or maybe even an electric boiler in your house. I think is used mostly in the Netherlands and maybe also in Germany. And the challenge here is in this central production facility you can make heat in a lot of ways. You can burn a lot of things. But some things are better to burn than others. So fossil fuels, we want to reduce CO2 emissions. So preferably we would not like to burn fossil fuels. Biomass is already a bit better, but yeah, maybe if it's better to use heat pumps with solar heat or even waste heat from industrial processes. And that's quite a challenge in operating such a plant. So when do you need to produce heat with which fuel? Also, heat demand is not constant over time. So that's why we have our software at Sigholm. It's called Aurora by Sigholm, and that is optimizing this energy mix and giving operators of this heat production plants clear instructions on what to do. So when do you need to start up your biofuel burner or a boiler, or is there going to be enough waste heat from from industry that we can use, and what's the best way to operate such a plant? But there, we also need forecasts for this, because we need to know how much heat is going to be consumed, how much heat is going to be needed for different parts in the city, and that way we can optimize our plan. There's also a lot of these plants also have it's called an accumulator. So that's basically a heat battery. It's a huge thermal bottle with water that's heated when there's a lot of heat production but not consumption. But can be unloaded when the demand for heat is extra high. And also that's an optimization problem. So when do I charge my heat battery and when do I unload this heat battery? Furthermore, there's also can be challenges. There's maintenance. So sometimes you want to use your biofuel boiler, but you can't because it's in maintenance. So what's then the best plan of action, and what's the best way to do this operation? And furthermore, we also provide follow-up of this production, because you really need to train the staff that is operating this plant. Okay, can we evaluate how did we operate, and did we operate optimal? And are there ways to improve it? So it gives feedback every day, so continuously. So you can get to an optimal operation as best as possible. You maybe have guessed it. So for this forecast engine, we use openSTEF. So that's it's giving really good forecasts for this. There's also some other things that do not really require forecasts. So a bit longer term, also do electricity plant trading. So sometimes you need to buy electricity on the market to also heat up, because they're in case of electric boilers. But sometimes these production facilities also produce steam and electricity. So then, we also do some optimization on bids on the electricity market. So there's, I think, a nice coupling also with what Bart told us. And on longer term, we do also fuel plans. So for the coming month, how much fuel do we need to buy to be secure of enough heat in the winter? So how does this look like? So often plan of Aurora looks like this. So there you can see the history. So there's different, each color represents a unit. So that can be this biofuel unit or even oil. So sometimes we need to burn oil. And on the left side, you can see this black line is the forecast in this case. And then all the other things are, according to our optimization algorithm, what's the best course of action. And this orange line you can see here is the value of the heat battery, so of the accumulator. So here it's best to keep it charged, and here you can discharge it in this operation plan. And then I want to show you how is openSTEF used in this. So this is one of our it's a heat forecast. So this is not electricity. So everything Bart showed you is electricity. But this is just for a city in Sweden. I cannot tell you which one, unfortunately. How much heat is being used. So that's the black line. And then the other lines are for different time horizons. What would be the forecast 24-hour ahead, or maybe even a 1 hour ahead. Or also something what is very important for us is when the electricity plan is sent. So when this bid is going out to the market. Any questions for, but I see some questions. Yes, yeah? Yes. No, we don't do congestion management yet. So that's not such a big problem in Sweden yet as it is in the Netherlands. But this could be one of the a great source of flexibility as well, because we have this heat battery, so heat can be stored quite long. So yeah, especially if we can produce and consume electricity on an hour's notice, that would be really helpful for flexibility. So yeah, good idea. Yes.
You were the first to apply openSTEF for heat forecast.
Yes.
Which was not done before, and I go back to the day when it was also not something was on mind when developing openSTEF.
Yes.
What's your experience adopting it to the heat case? It all worked well, and what
Yes, so we had our own forecasting engine before this, but we saw it was quite like openSTEF, so it was really great to be in this community. For the specific heat case, heat is also driven by weather influences, so it's same as the electricity nowadays with wind production and solar production. So here temperature is one of the major factors. Of course, that is, so if it's cold, a lot of heat is needed, and if it's not so cold, not. But also there's some social behavior also, because there's people using hot water for showers or in their kitchens. So that's also quite like electricity. So yeah, I found that it works quite well. It's quite easy to transfer. Maybe needed to add a little bit specialized models for these cases. But we also did some contributions to openSTEF to solve this to cover these use cases. So yeah, go find out in openSTEF if you're also interested. Contact me. So happy to talk. And so far it's really working really great. So this is running in production for I think we have over half of all the heat produced in Sweden is optimized using this software. So and also forecasted using openSTEF. So that's quite a big impact, you can say. Yes.
Yeah, and maybe you could talk about that you have different forecasting models, and if I'm not mistaken, openSTEF is based on XGBoost.
Yes.
Did you also directly compare this, and maybe from a forecasting perspective, but also from an application perspective, what are the differences that you mentioned?
Yes. So you mean comparing XGBoost with the other models for the peaks? You mean, or yeah. So that really depends on the use case. So here, this is more of a use case where overall accuracy is important. So not only the peaks. And I think if you have errors, it's okay, but it needs to be symmetric because we have this heat battery that can catch quite a lot of errors. So if there's a bit too low or too high, then there is some we can solve that with this heat battery. Just the peaks, I would not recommend using it for this.
openSTEF not only support one model, right?
No, it supports multiple models. Yeah, so it's not only XGBoost, but you can, if you want, also implement other models. Yeah, but XGBoost is really great for this kind of time series. So yeah.
In production, are you using different models and combining results, or what's your approach?
Yeah, we're using different models. Yeah, for different cities, different. That's very similar in how Alliander is using it. So they're also using a separate model for each site. Yeah. Any other questions? Then I think we have one more slide for action. These are a bit about our experiences. So we have increased forecast quality, improved maintainability, which is really great, and of course this community. So if you are interested in this, want to talk more, contact us through one of these ways, or find us on LinkedIn, or catch us here. Thanks.